Part 6, Scale Factors in 3D Objects. For this part, it is important to recall how to find the surface area and volume for the following figures. Surface area is the amount of space on the outside of a 3D object, so the sum of the areas of all the faces. Basically, if you were to paint the outside edges of everything, how much paint would you use? Okay, and then the volume is the amount of space inside a 3D object. So if you were to take a 3D object and fill it up with water, how much water would it take? Okay, anyway, so there's a whole bunch of different shapes here. So the cube, rectangular, prism, so that's a box. Okay, cylinder, cone, and sphere. Okay, there's the surface area formulas and the volume formulas for all those things. I won't go through them one by one because you guys can read, but there they all are for your reference. Okay, so remember that similar figures are proportional. Okay, so that means they have that same scale factor, right? The surface areas and volumes of similar 3D figures are also proportional. To see these relationships, we're going to compare the areas of corresponding faces of similar rectangular prisms as well as the volume. Okay, so we're going to try and make up some relationships here. Okay, so compare the surface areas of the following similar figures. So we'll start with that, and then B says compare the volumes. So we're going to compare the surface areas and the volumes of these two figures below. Okay, easy enough. So the first one, we're going to figure out surface area. Okay, now these are rectangular prisms, and they're as opposed to cubes because, of course, all the sides are different side lengths. So we're going to use this formula up here. Okay, surface area is 2 bracket length times width plus width times height plus length times height. All right, so good enough. I guess we should probably label who's who then. So I'm going to make this guy L. Okay, we'll make this guy the width, and we'll make the 2.5 the height. It really doesn't matter which of those you label what, because of course you can flip the box around or whatever, but it is helpful to put those on. Okay, so 2, and then length times width plus width times height plus length times height. All right, so the length we're saying is 5.0 centimeters. Okay, the width we're saying is 2.0 centimeters, and that dot I'm just putting there as a times. Okay, width we're saying is 2.0 centimeters. Okay, times the height, which is 2.5 centimeters, plus the length times the height, so 5.0 centimeters times 2.5 centimeters. All right, so when I type all of that into my calculator, I end up with 55 centimeters squared, or 55 square centimeters. Perfect. Okay, so easy enough. That's not so bad. Now, for the larger figure, we do exactly the same thing. So surface area equals 2 length plus width. Length times width plus width times height plus length times height. Now, you are supposed to put all the centimeters every time you write, but obviously I'm over half the page, so I'm going to need to write or condense it a little bit. So I'm going to cheat. You guys can't. Okay, so the length and the width, oh, again, same thing. So this is the L, this is my W, this is my height. So my length is going to be 8 times the width is 3.2 plus, now again, you should be putting the 8.0 centimeters. Okay, I'm just trying to save some room because I don't have as much on my tablet. So thank you for your understanding. I do appreciate. Okay, so the width is 3.2 times the height, so 4.0, plus the length is 8.0 times the height, which is 4.0. See, just enough space. Okay, now, when we multiply all that together, you end up with 140.8 centimeters squared. Okay, that's interesting. So, now, how we're supposed to, we already know the formula for this, right? We know that the k squared is supposed to be the area of the image, divided by the area of the object or the original. Okay, so if we have a quick look at this, like we should figure out what the K value is. So K should be, all right, let's look at the 5 and the 8. So if we go 8.0 centimeters divided by 5.0 centimeters, okay, that works out to 1.6. Okay, so then K squared, okay, should be 1.6 squared. So if we have a quick look at this, if we compare these, okay, so K squared should be 140.8 centimeters squared divided by 55 centimeters squared. So K squared, when you type that in, is 2.56. So then we square root each side, so then K equals, oh look, it really does equal 1.6. Oh, nice. So it works. It's functional. Okay, fantastic. So now let's compare the volumes of these figures. So volume is a much easier formula. So volume is length times width times height. So in this case, so 5.0 centimeters, and I'm back to the centimeters because I'm good for room. 2.0 centimeters, you should be writing that too. 2.5 centimeters. Okay, when you type this into your calculator, you end up with 25 centimeters cubed. Okay, then we'll do that for the second one, length times width times height. So this is 8.0 centimeters times 3.2 centimeters times 4.0 centimeters. Okay, when you multiply all those together, you end up with 102.4 centimeters cubed. All right, now we're not sure of the exact relationship. We can take a guess at it, but let's just figure out the volume scale factor. Okay, so we're going to take the area of the big one, 102.4 centimeters cubed, divided by the area of the small one, 25 centimeters cubed. Okay, so when I do that, I get 4.096. Okay, that's interesting. Now what we want to do is we want to try and relate that to this 1.6, to this scale factor. And I want to show you guys something. 1.6 times 1.6. Okay, that was the 2.56. Okay, so when I took the scale factor and timesed it twice, okay, I ended up with the area scale factor. So let's try it again. So 2.56 times 1.6, and look at what happens. Look at what you get, 4.096. Oh my goodness. So this 4.096 bit, that is K cubed. So equals K cubed. So that's crazy. So volume, so K cubed is equal to the scale factor, the volume scale factor. So very, very interesting. Okay, so if we flip the page, here's a summary of that. Okay, notice from the example on the previous page that the surface areas have a scale factor of K squared, just like when comparing areas, because surface area is just a type of area. Okay, but the relationship with volumes, we found that it was K cubed is the volume of the image divided by the volume of the original. So VI over VO. Fantastic. Okay. Just a quick little note before we do the examples. Remember when we're doing algebra on this, so that was, what did I say, 4.096. If I wanted to get the K out of that, remember you would cube root this on your calculator. Okay, that's how you get the 1.6 back. Okay, so it's for the area one, we use the square root button. For the cube one, we're going to use the cube root button. Okay, so example one. A smaller spherical water tank has a capacity of 1,400 cubic meters, while a larger spherical water tank can hold 4,725 cubic meters of water. Both tanks are filled with water from a pumping station at the same rate. That's important. Okay, so the water is flowing in at the same rate. How many times longer will it take to fill the larger tank than it will to fill the smaller tank? Okay, so the idea here is we just need to know how many times bigger the bigger tank is. Because if the water is flowing in at the same rate, then that's all that we're doing here. Okay, so all we have to do is we're going to compare the volume. So we take the volume of the bigger one divided by the volume of the smaller one to figure out how many times. Equals how many times bigger Okay, so that's pretty straightforward. So 4,725 meters cubed divided by 1,400 meters cubed. So when we type that into our calculator, we get 27/8 or 3.375. Okay, times bigger. So if it's 3.375 times bigger, it's going to take 3.375 times longer to fill that compared to the smaller tank. So I guess we should make a sentence here. It will take 3.375 times longer to fill the bigger tank. Awesome. And then B says, how many times greater is the radius of the larger tank than the radius of the smaller tank? So remember, these are spheres. So the volume of a sphere, okay, if we look back on that other page, it's 4/3 pi r cubed. Okay, so that's kind of what we're looking at. So if we're looking at that, now remember, we know the volumes. So what we're really looking for, radius is a linear thing. Okay, so really we're looking for the linear scale factor is the idea here. And if we're looking for the linear scale factor, that means we're just looking for K. And we know, because these are volumes, that K cubed equals the volume of the image divided by the volume of the original. So, and if we take the image to be the bigger one, so the volume of the bigger divided by the volume of the smaller, B for big. Okay, so if I do that, so 4,725 meters cubed divided by 1,400 meters cubed. Okay, so that's that same 3.375 that we had from before. So that's K cubed. So K cubed is 3.375. So now if I cube root each of those, okay, so then K equals 1.5 or 3/2. So that's interesting. So the radius of the bigger tank, whoops, missed a letter here. Bigger tank is 1.5 times larger than the smaller tank. Guess we should have a complete sentence. Awesome. Okay, well, that is it for this section. I need you to show your work and finish on page 500, question 1 and question 8 will be enough for what you need to show for this. So, thanks for watching. See you next time.